Okay, in this screencast, I'm going to review some basic trig identities, some of which maybe you should know, but we're going to review these because we're going to need these to integrate powers of trig functions. It's going to be one of our approaches. Okay, so the first main one is the Pythagorean identities. We can derive that by looking at the definition of sine and cosine, which is just a point on the unit circle given an angle theta in radians. Okay, and that's just going to display that the length from the origin to that point is exactly 1. To derive the other ones, other Pythagorean identities, you just divide each term, for instance, by cosine squared theta, and simplify, you get 1 plus tangent squared theta equals secant theta squared. That's the main other one we're going to use. To get the one involving cotangent and cosecant, you can divide each term by sine squared. The next ones we're going to also need is the even and odd properties of sine and cosine. So if we look at cosine and sine of an angle, okay, just for instance a point in the first quadrant, versus the cosine and sine of the opposite of that angle, right? Now drawing on the unit circle, you get these 2 points. Alright, now it's clear from the figure that if you drop this perpendicular down, they have the same exact x values and their reflections over the x-axis, so the y values are opposites of one another. Okay, therefore, we must conclude that the cosine of the opposite of an angle is the same as the cosine of that angle. Okay, in other words, that's an even function. It has the same value whether you plug a number in or its opposite, or an angle in or its opposite. Now, the sine has the opposite value, so it's an odd function. You get the negative by plugging in negative theta versus plugging in theta. The other ones, the next ones we're going to talk about is based off of this triangle. All right. Now we can see we've got a right angle triangle, theta in the lower corner, pi over 2 minus theta in the upper corner. Now what we're going to do is read off some of our basic trig functions. Sine of theta, for instance, is opposite over hypotenuse. That's a over c. Put yourself in the upper corner, and you get that cosine of theta is adjacent over hypotenuse, which is a over c. So what we conclude is that cosine of pi over 2 minus theta, not theta minus pi over 2, cosine of pi over 2 minus theta is the same as sine of theta. Now we can play the same game with the cosine. All right, if you take cosine of theta, you're going to get adjacent over hypotenuse, which is b over c, looking from the lower corner. Looking from the upper corner, sine of pi over 2 minus theta would be opposite over hypotenuse, okay, which is b over c. And we make a similar conclusion that sine of pi over 2 minus theta is the same as cosine of theta. Okay, so we can switch between cosine and sine if necessary using these identities. And that's going to be necessary when we derive the sum difference formulas. Okay. Now what you can further do, I'm going to just show one application of the last two combined together. Alright, so switching between sine and cosine, and then also the even odd properties. Alright, this will have a graphical interpretation also. Alright, for instance, starting with the first one, we know sine theta is cosine of pi over 2 minus theta. That's the first identity we derived above here. Now what I'm going to do is rewrite the angle inside by factoring a negative out. Alright, so take the negative out, you switch the order of subtraction. Now the even odd properties say that cosine is an even function, so you can essentially wipe this negative sign away, and you can just get cosine of theta minus pi over 2. So another identity says that you get the same whether you plug in theta minus pi over 2 to cosine or just plug in theta to sine. Now graphically speaking, that's going to show that this is the shift of the cosine graph right pi over 2. So if you shift cosine right pi over 2, you end up with the sine graph, as you can check. Okay. Alright, moving on. We're going to discuss the sum formula for cosine. That's all based off of this figure, the law of cosines in the distance formula. Alright, so I rewrote the law of cosines here. We've got two angles, u and v. I'm thinking about this angle in this corner of the triangle as the sum of u and v. These points on the unit circle. All right, as we have it pictured, this point here is going to be cosine u sine u by definition. Likewise, this is in the fourth quadrant, dropping down from the x-axis, so this point would be by definition cosine of negative v sine of negative v. However, we know from our even odd properties that this is the same as cosine of v. This is the same as negative sine of v. Again, you can pull the negative sign out of the sine. You can wipe the negative sign away from the cosine. Now, we're just going to plug into the law of cosines. All right, this length of this side of this triangle, we're going to call L. That's corresponding to the C in the picture. We get L squared is 1 squared plus 1 squared minus 2 times 1 times 1 times the cosine of the angle in between these sides, which is u plus v. Okay, so we simply just deduce that the length squared is 2 minus 2 times cosine of the sum of those two angles. To get the other expression we're going to need, we're just going to look at the distance between those 2 points. All right, if we square it, we don't get a square root, but we get the difference in the x components squared plus the difference in the y component squared. Now, when we take that difference for the y components, we're subtracting off negative sine of v, so it turns into addition. Now, all we're going to do is square each of these expressions out and compare it to what we got above, and that is going to be how we derive the sum formula for cosine. This is the cosine of a sum of two angles. So multiplying this out, we get the first term squared minus 2 times the product plus the last term squared, and similarly for the second binomial squared out. All right, now we're going to combine these cosine and sine of u's squared and v's squared to get 1 and 1. So what we're left with is that L squared, using the distance formula, we get 2 minus 2 times cosine u cosine v plus 2 times sine u sine v. Now all we do is take our first expression that we derived for the length squared, compare it to our second one, set both equal to another, and then isolate. Do a little algebra to isolate the cosine of u plus v squared. And then we have it. The cosine of the sum of two angles is the cosine of the first times the cosine of the second minus the sine of the first angle times the sine of the second angle. Okay. Now, from that one, because that derivation is a little bit tough, but a little bit of work to do. However, from this one and the previous identities we talked about, we're going to be able to derive the difference formula for cosine, the sum formula for sine, and the difference formula for sine. For instance, to do the difference formula for cosine, all we do is write the cosine of u minus v as the cosine of u plus negative v, and then put in u, leave u to be the same, but let v be replaced by negative v in the sum formula for cosine, and then use our even odd properties again. So this is going to be the same as cosine v in the first term there. This is going to turn into the negative of sine of v, which combines with our subtraction, flips it to addition, and that gives us our difference formula for cosine. That is, the cosine of the difference of two angles is cosine u cosine v plus sine u sine v. Okay. All right. Now we're going to be able to do the sum formula for sine in a similar manner. Okay, except we're going to have to flip over to cosine using our triangle idea. Alright, so that's going to be the same as the cosine of pi over 2 minus that angle. Now I'm going to rewrite this on the inside, distribute the negative through, and then group it as cosine of pi over 2 minus u minus v. And then this, we're going to think about this is our first angle, this is our second angle, and apply the previous identity. So that's the cosine of the first angle times the cosine of the second angle, what we're subtracting, plus the sine of the first angle times the sine of the second angle. Okay. Now these are going to leave unchanged. The sine of pi over 2 minus u is going to flip over to cosine, and likewise the cosine of pi over 2 minus u is going to flip over to sine, and that gives us our sum formula for cosine, or for sine, excuse me. We get sine of the sum of two angles is the sine of the first angle times the cosine of the second, plus the cosine of the first angle times the sine of the second. and the difference formula can be derived in almost the exact same way.